We're gonna start before 7:30 today. I'm gonna give you the recap on the last class. So this is okay if your friends are not coming yet. They have seen this in the last class already. The thing is that what's going on in the last class, I had the video recording, but the screen was just frozen for some reason, and then just my voice there without the picture. And the class before on Wednesday, I had just a picture without my voice, so I had to do a lot of re-recording of my classes, and that gives me a lot of headache. Anyway, so we can start. So what we talked about first in geometric nonlinearity is the stability function. So these stability functions basically is just something that you used to see for like the 12, 6 minus 12 and 6, 6, 4 minus 6, 2 minus 12 minus 6, 12 minus 6, and then 6 to 6 minus 6 and 4. So basically this is the stiffness matrix for the beam without the presence of axial force. So if we consider the axial force, then the entries in here will be all changed, subjected to the effect of the axial force. So your structure, the stiffness will be modified by taking the axial force into account. So we will look at the beam. First of all, we have a beam. Well, you just think about what we did in the first few classes. We try to obtain the stiffness, all right? Nothing more than what we used to do. We try to obtain the stiffness of the beam. But in order to obtain this stiffness, it will require the presence of the axial force. So we need to write the equilibrium equation based on the deformed configuration. Right. Previously, we did everything based on the original configuration. But now, once we look at the deformed configuration, we'll be able to account for the second order effect. So that's what we are going to do. So we will just apply the rotation or the displacement degree of freedom one at a time, and find out the corresponding forces and moments required to maintain the system in the given shape that we want. Okay, so let's take a look together. We will just set up the coordinate like this. Basically, if you want to come up with the stiffness matrix this way, you just neglect the axial force, and then you'll be ending up with the 12, 6 minus 12. All those things will be, well, it could be derived by this approach as well. So you can try that. But now we look at the coordinates. We have the x and y coordinates. So x indicates the location on your beam, and y is just the profile of your beam. That means if you differentiate your beam profile, which is given in the y direction, you'll be getting the slope. You differentiate twice, you get curvature, and another derivative that you get for the shear, and so on. So we can draw the deformed configuration. Well, if we apply some moment, so it is just our choice to apply, alright? As long as we cast the equilibrium equation correctly, you'll be able to get the stability function correctly. So I think that I'm gonna apply moment like this, and don't forget that this beam is subjected to the axial compression. We can look at the axial tension cases later. So the axial compression, the magnitude of the force is equal to P, right? I think maybe I just let this be the roller. So you have a good feeling that the compression could be applied, will not be taken, will not be absorbed by the support. So as we apply this moment magnitude M over there, then you get the deformed shape. But we will just first allow just the rotation only. We don't allow the displacement, we don't allow anything on the right hand side. Okay, we just do one at a time. So we now will start with the rotation. So as you apply moment there, then you get this deformed shape, right? And then this point here, I call it point Q, and cannot copy, so let me close this down. Let me reboot this. Okay, copy. Oh, it comes, the whole thing comes. Okay, fine. So here it is. We have this point Q. If we take a cut, so this is the cut of your cross section, cut of your beam, not the cross section. So with this cut, you have the moment, right? And you also have that axial force P. So this moment is given by MQ, right? And distance over here, this is denoted by Y value. Okay, the Y value is actually the function of X. But then from this point here, we cast the equilibrium equation. Don't forget, we have one more thing, which is the reaction, and I call it superscript A, right? Give some little more dimension. I'm just covering the part that we did in the last class, so just don't worry. This has been presented in the last class already. I'm just recorded again for those who come early. Then we can revisit the content we had before. So over here we set the equilibrium of moment. So sigma moment about point Q is equals to 0. So we take moment about point Q. We have the MQ, which is the internal moment from the beam, and then that adds up with P times Y. That adds up with M. That minus RH multiplied by X, which is the moment arm referred to your point Q location. Okay, so I did some sort of arrangement to make the MQ on the left hand side plus P times Y equals to X minus M, and the MQ is actually right now what I assume over here. This MQ, this moment MQ is going to cause the curvature like this, right? It is a result from this curvature, and this curvature, it is a positive curvature. Why is it positive? Well, this is a tangent slope, so start with low negative slope, zero slope, and positive slope, right? So the curvature is a change of your slope. So you can see that the slope changed from minus to plus. Your curvature is positive. So this moment here, okay, is associated with the positive curvature. We account for the direction of the moment in the equilibrium equations properly, right? Well, you might question that, hey, how do I come up with this shape of the beam like this? Could I derive from the beam coming downward or not? Let's say if you have the this shape in the green line in the bottom, can it be done? The answer is yes, it can be done. All right. So, but you just need to be consistent with the sign convention. So if it is going downward like that, your y magnitude will be negative. So when you cast the equilibrium equation, you need to account for those negative value of y in order to get the right magnitude and quantities in the equilibrium equations. So MQ, what is it? It is the moment at point Q, internal moment, which is caused by the EI multiplied by second derivative of y with respect to x. Okay, like this, where your y is the deformed shape. Okay, y is the deformed profile. So it's actually a function of x, is the deformed profile. deform beam profile. Now come down to here, plus P times Y. Well, we bring everything which is not Y, right, to that right hand side. So we have the RAX minus M. You copied this in the last class already, so don't worry, this is nothing new. I just repeat it quickly. Divide through by EI, so you have plus P over EI times Y. You add up with RAX minus M over EI and over EI for all. So I can just go quickly. And this term, we call it the K square. So 1K is the square root of P over EI. Well, then, if you call this 1K square, then second derivative plus K square Y equals to this thing on the right hand side. And you know that this differential equation over here, you'll be getting two components of your solution. So the first part is the homogeneous solution, which is YH, and that is the A sine kx plus B cosine kx. You have done this a lot in dynamic class already, you know. And then another thing is the particular solution, and that is the yp of x. For your particular solution, you can see these terms on the right hand side here, that your particular solution must at least contain the term with the x, right? So on this side, if you can see, this will not contribute the second derivative if it has the x, or well, it will give less x than this term, right? So you will expect from just the y term. So for the y term, the maximum order of x will be just 1x, so you have the cx plus d, right? So if you substitute this into here, you will for sure have this x on that right hand side. So this suffices for the purpose. So we need to find, well, we have A, we have B, we have C and D, but we will find C and D first. So in order to find C and D, let me just drop the Cx plus D into here. You drop it there, you differentiate twice. What do you get? Nothing, right? Because 1x, x to the power of 1, differentiate twice, you don't get anything. For this term, you plug it in, you will get the k square times the cx plus d equal to this side. Alright, so we will work on that thing. So I'll copy this term to the next page. K square cx plus d, right, equals to that thing on the right hand side. Well, if you want, we can replace the k square by p over ei. So I clear out this EI, right? And then C terms will be equal to this term, whereas this D term is equal this way. So you have PC equals to RA, so your C is basically R over P. And your D is equals to PD equals to minus M, then you get the minus M over P. Right? I substitute the CD into the solution we had. So we combine the homogeneous solution and particular solution into the same piece. So y function of x is equals to a sine kx plus b cosine kx plus c, which is a over p times x minus m over p. Look at this. Actually, you can cross-check your work a little bit. Well, what is the y? Y gives us the length scale, right? For the y, your solution y, because it gives you the deformed profile of your beam. It gives you the length scale, right? Then you look at the M over P. For M over P moment, which is the force scale multiplied by the length scale divided by the P force scale, you end up with the length scale. So that makes perfect sense. RA is a reaction force and P is also the force. Cancel, you get just the X, and X is in the length scale, right? So the A and B will be later the length scale for the A and B. Right now, we don't know about A, we don't know B, we have no idea about RA as well. We do not have idea about the M. That's what we have to determine. If you look at Kx, what is the K? K is the square root of P over EI, right? The EI, the E is a force per square of length, right? The E, elastic modulus is in the same unit as the stress, so force per like a unit area, and then multiply by I, then you get the force times the length square, force length square over here. Up here you have force, so force cancel out, then this is the 1 over length square, right? You take the square root, what do you get? Just 1 over length, right? This 1 over length is the K, and then you multiply by X, which is in the length scale. So the thing inside the trigonometry function is basically the Kx is the dimensionless. Okay. So I'll clean this. But for here, we can construct the infrastructure for the. So y prime, we differentiate the y with respect to x. Well, actually, I don't like y prime. I like maybe dy dx better. Quite clear. So it is AK cosine KX minus BK sine KX plus RA over P, and that's it. And you can enforce the boundary conditions. To obtain unknowns A, B, and RA and moment M, we enforce the boundary conditions. At both ends of the beam. So first of all, we know that Y, or your profile of the beam, as it is the support, pin support, Y at x equals to 0 is equals to 0. You do not expect any movement, translation in the Y direction at the support where the x is equal to 0, because over here, let me precisely specify this value. X is equals to 0 at the support, and over here the x is equals to L, which is the length of the beam, and your beam has the rigidity of the cross section being the EI, right? So we come over to here, we plug in 0, so 0 is equals to A times 0 plus B times cosine 0 is equals to 1 plus 0 minus M over P. So we say that B is equals to M over P. Alright, that's the first information we obtain. The second information, Y prime. Again, told you I don't like the Y prime. I use the dy dx, and then we evaluate this at x equals to 0. So I have AK times 1 minus BK 0 and plus RA over P, and that is going to give me the information over here, which is A equals to minus RA over P divided K, right? Minus RA over PK. Well, told you the unit of the B and the A was supposed to be in the length scale, length unit. So let's check. For the B equals to M over P, that is clear that it is the length moment divided by force. For the A, the R is the force, the P is the force, the K is what? 1 over length. So 1 over length, just go back up and then you get the length scale. So everything looks perfect. At least you should check something like this when you work. So now for the number 3. Oops, sorry, wait 1 second. I just need to change something with this. Okay. Sorry, at this point B, no, at the point x equal to 0, we have rotation. Sorry. Okay. We have rotation. Let's go too fast. Okay. Let's go. So, theta is there. And the theta is there, then we equate this to theta, and then we want to put the theta, right? The theta is on that. Okay, let me move it out a little bit. So theta, okay, we add the theta in. RA will be later, and then okay, over K. Makes sense, right? Because the theta is dimensionless. Dimensionless divided by 1 over length, you end up with the length scale. Right, so we move forward to the next support. The next support, the condition number 3. We have the Y evaluated at L equals to 0. So we have 0 equals to A, which is the theta over K minus A over PK. What is it? Sine, right? It is the sine KL. Plus, for the B, it is the M over P cosine KL plus RA over P times L and minus M. So we have everybody on board right now. Number 3, we end up with this shape. Right. Let's manage, group things up a little bit to make life beautiful. This M over P, right? Okay. Okay. So let's start with the easiest thing we have around this neighborhood. The equal sign. Okay. M over P out there, just group them up. M over P, so we have the cosine KL minus 1. And then we group up the R A over PL. RA over PL was supposed to be 1, right? We take one from here and another from here. So 1 minus, this is RA over P. We pull it out, we pull the L out, then we get the sine KL over KL. So what else? Done, and done. Right? We have only just the theta term. So plus theta over K. Okay, theta over K sine KL. Basically, I will not leave the K alone, okay, but we'll be able to fix it. So all of them are having the length scale. We move forward to the next equation. Class number 15. So number 4, dy dx evaluated at x equals to L is equals to 0, and then 0 is equal to can I just copy these terms and I'll just make some modification, because I know that so for sure we don't have the M over P term there, we don't have L here, we don't have sine here, right? We have cosine, and we have the K in front of this cosine function, right? AK cosine minus BK sine BK sine, right? And then plus RA over P. That's it. Regroup. So well. Okay. RA over P. L. Okay. RA. I just multiplied through the equation by L. Alright? This is the equation that controls the slope. Previously, we have the equation that controls the location, the deformed profile. We are going to set these two equations, we are going to equate them in order to solve for the remaining unknowns. Remaining unknowns for now, what do we have? Theta is given. Theta will be known. So the unknown will be just moment and the reaction RA. Okay, so we will make use of these remaining two equations at point L, x equals to L. So I scale this by multiply through by L. So over here you have the RA over L or RAL over P, and that is 1 minus this term. You pull out RAL, then you get one second. Okay, so K here cancel out, right? Alright, fine. RAL over here, okay, great. So this makes you cosine KL. What's wrong with that truck? M over P, and then in the bracket KL sine KL. Previously you have just M over P out there. We keep the length scale out there, right? M over P KL sine KL, and we try to keep everything inside the bracket or parenthesis to be dimensionless. So the terms with the length scale dimension is just in front of the dimensionless term inside the bracket. So R is there, M is there, then we have the theta plus theta cosine KL. Theta L, right? Theta L cosine KL. I multiply through by L already. Then theta L cosine KL. Two equations here and here. For here, I think to make it consistent with what we just made, I have theta L and then divide by KL. Any objection? Previously it was the theta over K. So now I just push the term K inside the bracket, but K alone it has the dimension, so it makes KL, and then I have the delta multiplied by L outside. I just multiply and divide out by the L, so that is perfectly legal for mathematicians, right? Theta L, so everything's there. Then we will equate these two equations. So let me copy this, put here. Basically, as the theta is going to be the known value, we open up. We just need to set something to be known. So we open up the angle to a given theta value, so theta will be known. But then what are the corresponding reaction forces and required moment to rotate this beam under the presence of axial force P to this angle, precisely theta. Alright, so theta is known. We need to find out RA and M. Maybe we can do many things. First of all, we write theta in terms of RA and M, and then you'll be able to make the relationship between RA and M. Okay. Another way, we write M in terms of RA and theta, and then you'll be able to write the relationship between RA and theta. Okay. So whichever, let me take a look at it. Well, it would be painful for all of them, because you can see that it just looks scary here. So I'll do it this way. I'll put this in terms of RAL over P. You just need to call the garage. You're not going to make that truck work and run out of the lab. This is the 20th attempt. Okay, I put some Greek letter in here. What could that be? Okay, so this stands for 1 minus cosine, and then minus M over P omega plus theta L so the M over P is given by 1 over omega okay, we put M over here. Okay, R A L over P plus theta L alpha. The thing is that I just don't like to have that monster sine cosine functions fly over. The terms are very messy. That's just the thing. I try to facilitate our life. And for here, 0 is, this is artificial 0. Okay, 0 is equals to M over P beta plus RAL over P times the plus theta L times new get all the Greek letters I can think of. So basically M over P is going to be minus 1 over beta, and then these things in the bracket. Okay, so I can equate these two, right? As I equate these two, I'll be able to write the things in terms of one another. So right, we will just put all these things, substitute the value of alpha, omega, all Greek letters will be replaced later when we work on the worksheet Microsoft Excel. But for now we're gonna keep them like this. You have -1 there. Okay. So -1 will be there and there. Then we distribute that terms. What should we move? Okay. Minus RAL over P multiplied by gamma minus beta over omega C. Whereas on the left hand side we have the theta L plus alpha beta over omega. We can cancel out the L for now. Let's count how many times that Jesus. Okay, now let me distribute the negative sign here inside. So negative sign there will be okay. It look like this, and then what? I will write the RA in terms of theta, and that is given by theta multiplied by this term and then this term. Oh, strong. What else? You have the P, right? Theta multiplied by P multiplied by eta and alpha blah 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 divided by these things. Okay, and then from P we don't want to keep this shape P like this. If you recall, the K square is equals to P over EI. So the P is equals to K square EI. I'll be replacing P by this K square EI, right? So P is gone. K square EI. I put it here instead of P. Well, we are about to write the reaction force R in terms of theta. Previously, this R was supposed to be 6 EI over L squared theta. In the case that we derived before without the axial force. But now if you write the R in terms of something theta and P, who is this P? Okay, it looks just not consistent with things we used to do before. Yes, you can keep the P there, but it is very funny. So I just put the P in terms of EI, function of EI. So it is K square EI. K square EI, well, when I see the K, I've tried to push the K with the frames of K. So K will be going inside with the dimensionless term. But to make it dimensionless, I multiply L square over L square. So that makes the theta EI over L square, and then the KL square will be pushed inside the bracket. So the KL square multiplied by this term. Oh, it's running out of space. We'll put here then. That is equals to RA. So it looks scary a little bit, but we let Excel work on this business. We need to find the MP as well, right? So the MP is given by either this function or this function. Whichever you want to play, you can select just one, but both of them will give you the same will bring you to the same destination. So I will pick the first one. M over P is equals to 1 over omega blah blah blah. I'll copy this. Yes, anything? Beta here, okay. So beta over omega C. Which C? You mean alpha or what?
No, beta over omega.
Beta over omega.
Yeah, that one.
Should it be negative?
Yes.
Huh? Okay, let me check. Beta over omega. Alright. One second. Okay. From which line then? Line number 2. Beta over omega. This line. Okay. I move from the left side to the right side. So I need this minus. And then this is also, and this is also minus. Okay. Thank you. Okay. So I'll bring these guys what is that thing? What is this one or what? Why do I put it here? It's nothing, right? Okay. Paste. Okay. So we need to substitute the RA. I will first clean up the P. The P is gone over here. The P is there. Okay. And the RA will be substituted by this whole thing. Anyway, we don't really have to substitute because we're gonna work on the RA first in the Microsoft Excel. So the RA will be left there, RAL. Okay. No, actually it is not bad. Yeah. And then for the theta term, theta times L over P. Okay, and the P is again theta L over P. P is K square EI, right? Theta over P. Oh, no. P has to be up. P is not the denominator. P is here. Up there, right? Because we just multiply through by P. It used to be M over P, used to be RA over P. So it has to be up there. Yeah. Then P is K square EI alpha. So I give you the extra L. I mean, I do it here. Okay. So I have the L square over L square. In order to bring the KL square along with the dimensionless term and leaving just the final shape, it's gonna look like RA L over omega and then plus theta times EI over L. Yeah, theta EI over L, and then I take the KL square inside, KL square goes inside, you have alpha there and omega. Right? Which is equal to this term RA multiplied by L so RA multiplied by L and multiplied by C over omega. Alright, and then plus the terms on the right hand side here. So, yeah, moment is given by theta multiplied by EI over L multiplied by one coefficient, dimensionless. You think of 4EI over L. For the force, it's given by theta multiplied by 6EI over L. But instead of 6, that dimensionless terms is going to tell you what is it. Aside from 6, okay, 4, 3 or more, depends on the force that you apply to your structure. Now, you have this M and RA. Let's look at the structure in order to find the remaining forces and moments. You keep in mind that first of all, the force equilibrium in X is already satisfied. So if this is the M, if this is the A, vertical force equilibrium has to be satisfied, right? So you have the RA, of which the magnitude is opposite from the RA on the left. Okay, so reaction, vertical reaction force on the right goes downward. for a moment, if we set up the direction of your moment like this, if we call this guy the MB, so right end is equals to B, so we have the MB plus M minus RAL equals to 0, right? MB positive, M there, and RAL going into the opposite direction, so that is equals to RAL minus M. The P doesn't contribute in this equation because now we are considering the whole structure. We are not looking at the internal moment. So the P delta effect is actually absorbed in the M already. The P delta is there. But this picture, the force at both ends, they are concentric. So that doesn't produce any moment. It produces the internal moment. Right, but in the big picture it doesn't. So MB add up with MA going in the same direction minus RAL equals to 0. That's all we have. We don't have any externally applied force, distributed load or anything like that. So that is all you have in this problem. Okay. Now, we will continue number 15, page number what? Number 4. We will make the table of this stability function. The part you have here, you would supposed to get number 4 if we don't have axial force right? 4EI over L times theta. That's what we're supposed to get. And for this part, I push it too much on the so this thing here was supposed to be six or P0 or the KL is approaching to 0 because the KL is the P square square root P over EI, so that will be identical. Then we're gonna plot. We will plot the stability function. I try to talk about everything on this iPad, and then once we move to the PC, then I don't want to switch back here. So we'll plot this. It will turn out to be your homework, well, for sure. So the y-axis is the value of your from your stability function. The x-axis, well, in order to write the stability function value as a relationship, well, you can write it in terms of P or KL, right? Because that controls your stability function. The thing is that if you write the stability function in terms of P, and if you don't know anything about your cross section, then that doesn't give you any sense, and it could be applicable to just one member, right? Because maybe this column and the P is 1 metric ton, it is a small value, whereas this column 1 metric ton could be a very large value. So you will need to try to normalize the value in the x-axis such that it is universal. It can be used for all the columns, but what you need to drop in the x-axis will be something. Okay, well, the KL could be used, but again, the KL is still difficult for us. The K is the square root of P over EI. You don't have the feeling about what is the P over EI. The P over EI equals to 1, is it big? Or P over EI equals to 10, is it big? No idea. Completely clueless. So, the axis X, generally we will use the P over PE, where the PE is the Euler buckling load. We will derive for this Euler buckling load, but for now we are still talking about the stability function. I'll just tell you first. So for Euler buckling load, if you have a column like this, and then we call it PE. This column, the length is equals to L, and you have the cross-sectional property EI. So Euler buckling load PE. Actually, we just use these derivations. We set up the y equals to the differential equation. We solve differential equation. We solve for the boundary conditions, and then we enforce the eigenvalue problem, and then we get the PE, right? So be patient, wait a bit. You'll be finding that it is equals to pi square EI over L square. The L is the effective length, so at the buckling you will find that the shape is like a half sign. Okay, so PE is given this way, pi square EI over L square. So P over PE, well, you got to think, in the function you derive, you write everything in terms of KL, right? So you need to express the KL in terms of P over E, or be able to find the link between P over PE and the KL. So P is equals to K square EI. K square is equals to P over EI. And then you divide P by PE, which is pi square EI over L square. Then you cancel out DEI and DEI, and then you push the L square back up to the top. You have the KL square over pi square. Basically just put the KL over pi and square it up. Okay, so that's your P over PE value. So when you work on your calculation, you're gonna formulate everything as a function of KL, and then you will translate the KL into the P over PE value later in the next column. Then you can plot your stability functions. Whatever, how it's gonna look like will be continuing in Microsoft Excel. And then we finish up this case. We'll be doing the next case where we apply the displacement. Okay, and done. And we do the tension case. So the stability function we have will accommodate our scenarios. Over here, P over PE pointing towards the positive x direction means the compressive force. Tension, we will be putting it on the left side of the graph later. Okay, let's have just a very short break. I'll stop here before we start the Microsoft Excel. Right. 5 minutes. We start now. We switch to Excel to construct that stability function Basically we need the KL. We use the KL. That KL will be later on computed into the P over PE. I put the boldface just like this. Now I think this is just a systematic way of doing things. If you stuff all the equation in just one line, most of the time you get it wrong. So doing things in systematic way, okay, you design the architecture. Sometimes you do the same job as your friends, but the one who can design the architecture of work better ends up with the better result. So less error, more accuracy. And this is about the architecture of this workflow. So we need the psi KL. That'll be calculated in sine KL, cosine KL. I just make this KL is 0.0001. Okay, fine. Everything just going to be 80. Okay. This is fun, huh, to okay. All right. P or PE is equal to what? Pi what? KL over pi, and then you square this up. Okay. Okay. Keep it this way. Fine. So this is equal to sine of this. This is equal to cosine of this. We want to start with the stability function for the RA. So I will call that S6. S stands for stability function, 6 stands for, it was supposed to be 6. Yeah, so it is just easy. Sometimes people use the S and C and SC. You can find that in some textbooks about stability. Stability textbook. But I don't want to memorize what is S and what is C and what is SC. So I will just go with like S6, S4, S12, like that. Okay. So we look at the RA, which is equal to theta EI over L square multiplied by, in the bracket, KL square eta plus alpha beta over omega, etc. 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 So let's start with eta. Okay. Eta is like the N, right? Alpha, beta, omega, C, gamma. 1, 2, 3, 4, 5, 6. Yes, we have all 6 here. So let's start with the if we look at the boundary condition number 3, we have the beta there. Beta is equals to cosine KL minus 1. You can see that the number is not so friendly. 1 sometimes very close to 0. Beta, alright, beta is cosine KL minus 1. Next, the gamma is here. gamma is equals to 1 minus sine KL, and then divide by KL. Then we get the gamma, and eta is equals to sine KL divide by KL. If something goes wrong, then it is very easy to track. Next, C is equal to 1 minus cosine KL omega is with m over p. It is KL multiplied by sine KL. Let me check the sine of omega. Okay, so I make the m over p equals to, alright, okay, so the sine of omega is correct, it is positive, like that. And the last one, the alpha term is, basically just alpha is a cosine, right? Cosine KL. Okay, so S6 is equals to, right, a huge KL square multiplied by eta plus alpha times beta divided by omega, and that is the numerator. Denominator is minus beta times C divide by omega, and then minus gamma, close the bracket, and I guess that is pretty much it, and it turns out to be 5.99999996, right? Relief. After a long derivation, then we compute this, and then what is this number? We have S6. The next is going to be the S4. So for the S4, let's see. We have the long. We have the KL square. Basically we can use that as the additional part is the C over. Okay, so this is equals to the C over omega multiplied by the S6, right? C over omega, and then the rest is the S6, okay, and then plus KL square. KL square again. Alright, fine. KL square multiplied by alpha divide by omega, right? Yeah. Okay. And then this is a number which is really close to 0 if you drop 0. Let's see. The stability function, as you can see, it involves a lot of sine, cosine function, divide, denominator, like that, and you might end up with this issue. So you can get the value for your function when it is very close to 0. If you want to evaluate the actual value when it is 0, then you might need the L'Hopital's rule, because Excel doesn't carry out that calculation automatically. But well, if you want, you use L'Hopital's rules. The thing is that this is not quite friendly for the computerized structural analysis, because we have some sort of exception like this, and that is quite inconvenient for our life. So that's why this stability function, well, you get a very accurate values, but not widely used. If you compare with the geometric stiffness matrix, which is the simplified version, that one gives you a better result, because it doesn't have any sort of jumping of the function like this, divide by 0 or approaching to infinity. So that is embedded as a part of the structural analysis program. Like I think SAP used the geometric stiffness matrix. And then you just vary the given value 0.1, and then you can find the corresponding POPE value, which is still very small for now, so you can keep going. Oh, 18, too much. Let me see where to stop. Probably around, yeah, 4, 5, 6. Yeah. And then done. Actually, it should be homework. It's nothing, right? but if it is homework, then you can end up with this for 5 hours trying to get this thing to work. But it works. You should do it, because if I just give things like this to you, then your learning curve is not coming up. Things you see that looks very nice and easy in the class, as it might be your first time, it is not that easy and smooth. Here is the stability function for that S6. So you add format. Wait a minute. Text option number and just number. Okay. Yeah, when you plot something in homework or assignment, handout, things that you submit, just don't leave it like that. That shows that you are a sloppy person. I don't know. I judge people like this. So if you leave it like that, like what? Leave it like this, scientific, or some crazy things. Just clean it up. The program just give you automatic values, and if the extent is up to 6, then you just need 6. I don't know why we keep that space in here. Okay, add in select data, we add series name, x-axis is this thing here, and the y-axis is this one here. Yeah, you can see here. So at this point it has like a jump, so the behavior, well, kind of not so stable at this point, and it switch around. You have some behavior pretty much like a snap through. It is not the snap through, but something that you have the stiffness switching the sign. Okay, so that's why we don't like to use this in the computer program. Let's format this again. The axis, this extend is too much. What, minus 6 minus, okay, 12 and 12. Okay, we use it in just this region, so you don't need to go up to the infinity and then you cannot see anything down here. You can even just put this in the format plot area, you know, change it as delete, well, move chart, or what is that? Yeah, new sheet. Okay, right. You put it in here. If you want, you can add the elements like the axis, primary, well, primary, grid line. Okay, yeah, that's gonna help you. Looks better. What else do we need? Axis title we don't need, chart title we don't need, label don't need, error bar, grid line, legend, no. The trend line we don't need it now. Okay, right. Along with the table there, then you can perform structural analysis because you will know the PO/PE ratio. So the force, axial force in your member will be determined. In structural analysis, many cases we don't know this ahead of time. We need to perform some sort of iterative calculation. So you estimate, you assume the axial force P first, and then you come up with the PO/PE ratio. You get this PO/PE ratio, you find the S4, S6, S12, S2, right? Plug it into your stiffness matrix and then conduct the structural analysis. Once you finish the analysis, you'll be able to find all reactions and internal forces. Once you find internal force, internal axial force, you will check if it match with your assumed force or not. If it doesn't match, then you will get the new the value that you just calculate for the P axial force value and put it in here. You find PO/PE ratio, you find the stability function, you run analysis for another time, you will get the new axial force approach. Okay, it will converge to your analysis result. So first round you assume, let's say 0. Okay, you finish the first round analysis, you get something like 5, and then you use this 5 and come up with the new stability function and rerun analysis. Once you finish, you might get like 5.5. Okay, so value will converge to the actual value, the final solution, but you're gonna need like a few iterations, like
3 to 4 iterations, and then you'll be approaching to one value. So we will do that, don't worry. You might not be able to imagine at this moment. We will do that. Okay, so this take us like shorter than I expect, so we will switch back to the derivation of stability function for S12. Okay, so we stop this one here. So we continue.
Sure.
Yep. What you have to do in your homework? Plot, yes. What values? Well, you just go ahead with the KL, right? And then use the KL increment. What? Make it like this. Make the P or PE value increment being 0.05. Okay, let's do it this way. So 0.05, that means 20 increment for 0 to 1, right? 0.05. So from 0 to 4, then you have in total 80 increment. At the 0, you cannot put the real 0 there, so you need to put like 0.0001. Okay, as long as it gives you the number, okay, you can keep reducing it down, right? So you have in total 80 values for each stability function. Extend the POPE from 0 to 4. For the vertical axis, you extend from -12 to 12. All right. So that should be clear. And you plot the graph, and you also document that table of stability function. When you print out the table, you don't necessarily have to print the value of gamma, beta, because it is useless. You just need the S12S whatsoever. Maybe you might show the corresponding KL value, KL which correspond to the increment of your P over PE, right? So you can set P over PE and then compute KL. That will be different from the procedures I show there, that I come up with the KL and then find the corresponding P over PE ratio. Okay. Now we move forward. We have about half an hour from now. Let's take a look at the case where we have this. Oh, no. So this case, oh no, this side is supposed to be we have the axial force like before, apply like this. We have no idea about the direction of the
reactions, then we assume the R at point A like this. You have no idea about moment as well, and it is assumed this way. We set up some point which is called point Q like before. I don't like the green line. It is Rồi. Terrible. Okay, so we follow the step we had before. This problem, actually we can think about it this way or the other way. Which is equivalent. The point is that if we just do it that way, it is just not convenient for me. You know, you will have the point force going like this, and the moment arm for this point force will be this one, which is the delta minus the y. Not convenient for me. I don't like it. So I will say that, well, if we think of it the same way, well, pretty much the same, but not exactly the same. So the beam will be deformed. Okay, not satisfactory for me. Sorry, I cannot let this go. Okay, and then I scale it out. Okay. So what if you apply this? So let this side come down. So move it down. Actually, what happened is identical. So that one seems to be going up,
but we actually move this relatively downward, just that.
And then this is known to be delta. The beam at this point, x is equals to 0 and x is equals to L at that point. Positive sense of x is towards the right hand side, nothing changed. Positive sense of y is upward, it doesn't change. So this is y. Okay. And then we're gonna take a cut. So the point that we take the cut is somewhere over here, and that is point Q. Can I just write something? This is called the original configuration, and the green line is called deformed configuration.
The essence of the stability calculation of structure, or the P delta effect, second order effect, is that all the equilibriums are written in the deformed configuration, right? That's the only thing that was different from your study before. Okay, I will there must be the tool that help create the curve nicely. So your x is there, y, x, y, your point Q is here. I'll need the this is equals to x, and this is function value y, right?
P and P. What color? Purple? Depends. If you want to write the moment like this, you can. I'll show you how to make it work. The consistency of the sign has to be there. So this is the MQ. RA. We need RA. Is also there. The moment M, we assume the sign like before. Okay, we are ready to move. So based on this picture, we cast the equilibrium at point Q. Given that this is positive sense of your moment, so sigma moment is equals to 0. So at point Q, you have the MQ, which is going into the positive direction. You have plus M, you have minus RA multiplied by X, right? And the last one is what? Minus P, right? You take moment here, and this force P is going to cause this moment, which is opposite to this direction. So it is minus P, right? Minus. Okay. The point is that you need to put that negative value in, but your Y, okay, you have over here, the Y value has to be neutralized first. You address the sign already, but your Y could alter the sign of your equilibrium. Okay, so Y value, when the point is below the x-axis, Y value is negative. So you need to put the negative in front of the Y to neutralize the sign out. So it is the minus Y. Okay. Otherwise, your moment direction will be changed by the position Y. So we neutralize and make sure that Y turns out to be one positive number. P is that number, magnitude. P times Y, you get the magnitude, and then the minus sign account for the clockwise direction, which is opposite to what we assume, what we set up for the sign convention.
So what about the direction of MQ?
The MQ, I put, oh yeah. So the direction, MQ is negative. Thank you, yeah. Correct. Everything is there. I think we have all equals to 0. Right now, this time we assume the direction of MQ into the opposite side from the one we worked before. And the first thing, we move the AX minus M to the right hand side first. Over here you have plus and plus, then you minus and minus, then you get plus PY. MQ is negative, okay? Then you have the minus EI, and then multiply by curvature.
But if you look here, this curvature is a curvature that cause your beam goes like this, from positive slope to 0 to negative slope. That is the negative curvature. The negative value will change the thing in here, right? So we need to put the minus sign in front of the derivative of y with respect to x in order to neutralize the value, neutralize the sign that you have from this curvature. So that neutralizations bring you to the positive y x plus p over ei times y equals to rax over ei minus m over ei basically the governing equation doesn't change. You set it up on above, okay, the side which is above the x-axis, or you set it up on the side that is below the axis. It doesn't really change, as mentioned, as long as you are consistent with the sign convention. Now I think we do not have to repeat that particular solution things. Okay, I just get the form for the homogeneous and particular solution from before, and I'll drop it in here. So this solution we have is in this format: ax bx rax m over p. Okay, we don't waste the time there. Move it down a little bit. Then the next step, is to enforce the boundary conditions. So start with the first one. Well, this time it is quite easy because the boundary condition on the left hand side are all 0. So with the first one, y 0 equals to 0. That makes your b equals to m over p. 2 dy dx at x0 equals to 0. That makes your a equals to let me go check what should be the a. The a should be RA over PK minus the third one, dy at L is equals to minus delta. What time is it? 54. Got to run out of this room real quick, guys.
So this is going to be the last line that I make for this class. Minus delta is equals to okay, minus delta is equals to all these things. So we will work on it. Oh, yes, yes. Great. Thank you. So we continue from this point in the next class. Tomorrow class will be on the programming. So we will learn the architecture of the computer structural analysis programming. So we switch to another mode. But still it is 7:30, so we'll try to push it up. Okay. Alright. I'll upload this video and the class note, but without Excel file. So you do it by yourself. Okay. See you tomorrow.